In our previous section, we looked at fitting polynomials to our data to interpolate between points. So for example, if we had n plus 1 data points, we could construct an nth order polynomial. Let's just call this fn of x. But what you should have seen as well is that there are cases where we could end up with erroneous results. So think about when we had inverse data sets and not evenly spaced data, we ended up with telescoping, and that caused oscillations within our polynomial. So an alternative strategy would be to perhaps apply lower order polynomials between the points and in order to interpolate between the points. And this is called using spline functions. For example, a cubic spline is a third order polynomial that's fitted between data points. We constrain these spline functions between the points, for example, that there must be a smooth transition between different regions. So let's just demonstrate this with a simple figure. Let's say that we have a function that looks something like this. We can call it a square wave. So it looks something like this. So now that is our actual function. And let's say that we have 2 data points from our observations. At each different section. And I wanted to fit a second order polynomial. I might end up with something that looks like this. So this is a quadratic fit. And you can see that there's some overshooting in some regions, and it doesn't quite capture this vertical jump in my function. But it's not bad. But so now I want to try and increase the accuracy of my polynomial. So I end up finding more data points. Let's say we add a third data point. And that means I can have a higher order polynomial that may look like this. Now, again you can see the overshooting in our function, and it doesn't quite capture the data points. So within these regions where there's overshooting, we're not capturing the trend of our data, which is problematic. So we try again, and we say, okay, let's increase the order of magnitude of our polynomial, and we use another point. So now we've got 4 data points on each side of our transition. You're going to end up with a polynomial that's going to look something like this. And again, we have some overshoots. So we haven't actually resolved anything. We've just made the problem worse. Well, what if I took a linear approximation between each data point using what I termed earlier a spline function? So let's say a linear spline function. Well, I would end up with a function that looks something like this. Let me just redraw my axes. Okay, so I would end up with a function that looks something like this. Now, although I might not have got this transition section correct, I have got the majority of my function being well described by using linear spline functions between each data point. So I can write this mathematically to say that a linear spline, which is the simplest spline function, and effectively we're connecting our data points with a straight line, can be written as, let's just change the, no, let's leave blue. Blue is good. F of x is equal to f of x naught plus m naught x minus x naught, where x is between x1 and x0. Okay, and this would go to our nth data point. F of x is defined by f of x n minus 1 plus m n minus 1 of x minus xn minus 1, where x is between xn and xn minus 1. And the gradient, or the slope of the straight line connecting the points, m, for my ith spline function, is equal to f of x at I plus 1 minus f of xi. And that's all divided by x I plus 1 minus x I. So now we can describe or evaluate our function at any point between x0 and xn by first locating the interval within which the point lies. Then we derive a suitable or appropriate equation and solve accordingly. And this is obviously very identical to linear interpolation. So let's look at an example.